Hello and welcome to another Smart Grid Systems class. Today we begin power flow. Power flow is the standard steady-state analysis used in power systems to compute bus voltage magnitudes, voltage angles, and then real reactive power flows on every line and transformer. Today's workflow would be to model the network, build Y-bus, write power balance equations, solve and compute flows, and also losses and violations. By the end, you'll understand what the solver is doing and why. Now, everything starts with admittance. If a line has impedance of Z equal to R plus JX, then its admittance would be equal to Y is equal to 1 over Z. In other words, we can write it as Y equal to G plus JB. Now, G is the conductance. It's tied to real losses. And B is the susceptance, which is tied to reactive power and voltage behavior. Or in other words, it's the imaginary part. We use admittance because nodal analysis uses the form I equal to Vy, and I'll explain more about that. Maybe bring up my pen. Sorry. Yep. So again, as mentioned, Y is equal to, or in other words, we can write it like this: Vy is equal to I. And as you already know, impedance is equal to R, which is the real part, plus Jx, which is the imaginary part. And Y is equal to 1 over Z. Now, big admittance means a strong electrical connection, means we have less actually impedance, because the higher the impedance is going to be, the lower our admittance would be. And you're going to have better connection, better conductivity between them. And a small admittance means we have weak coupling. Now we go from one element to a whole grid. We represent the entire network with a single matrix called the Y-bus, the bus admittance matrix. Once Y-bus is correct, the rest of power flow is basically solving equations built from it. Now, a Y-bus is an n by n nodal matrix used for power flow and steady-state network calculations. There's also Z-bus, the bus impedance matrix, which is conceptually the inverse of Y-bus. Again, Z-bus is the inverse of Y-bus. Y-bus is often used in fault analysis because fault currents relate naturally to driving point impedances. For power flow, we stay mostly in the Y-bus, or because it's sparse and efficient, and it's easier to solve, much easier to solve. Now, the bus structure is very systematic. And off diagonal Yij represents the connection between bus I and bus J. So if we have two buses, I and J, the connection between these two is represented with Yij. If I and J are connected by a line, Yij equals minus the branch admittance. If they're not connected, it's 0. So if here we have, I'm going to show the admittance with Yij, then the capital Yij would be equal to negative Yij, or the admittance between them. If there's no admittance between them, it's going to be 0. Now, diagonal Yii is the sum of all admittances connected to bus. So if we have Yii, it's all them everything connected to this bus, for example, bus I, including any shunt elements as well. And I would show you this with an example. Now, this example, this shows the nodal admittance matrix. This is Kirchhoff's current law in matrix from I equal to YV, and I is the nodal induction current, V is the nodal voltage, and Y is the nodal admittance matrix. For a line between I and J with admittance Yij, we set Yij as mentioned is equal to negative Yij, and this is the admittance between the bus I and J. Add that same Yij to both diagonals Yii and Yjj. So these are Yii and Yjj, and any shunt at bus I is added only to Yii. These rules let us build Y bus directly from the line to one line diagram. So these are the ones that are connected only to this, and the same is over here as well for all of them connected to this bus admittance. And I would explain it with an example. It will be less confusing. Now, the point here is that lowercase y is physical admittance and uppercase Y is admittance in the bus. Now, this is an example of a 2-bus system. It's a 2-bus example. And here, again, Kirchhoff's law is YV. And to solve this 2-bus example, if the line admittance is Y12, then Y12 would be equal to Y21, which is the bus admittance, which is going to be equal to Y lowercase y12, negative y12. So each diagonal is the sum of connected admittances. So y11 would be equal to y12 plus y11. So everything connected to this bus is going to be y12 and y11. And we're going to have the same thing for bus 2. Y, and this is capital Y. Y22 would be equal again lowercase y22 and lowercase y21. So it's going to be y12 plus y22. Now this is all the admittances connected to bus 1, and these are all the admittances connected to bus 2. This is the pattern you'll use for any system size. And let me erase all of this so you can see how it's done. So again, y12, the bus admittance, is going to be equal to negative the negative of the admittance between them, and y11, the bus admittance, would be all the admittances connected to bus number 1, which is y12 and y11. Same thing for y21. It's the admittance between these two bus, which is y12 or negative y12 in other words. And finally, for bus number 2, all the bus admittances connected to the bus is going to be y12 and y22. So y12 plus y22. Now let's solve an example for a 3-bus setup. We want to create the nodal admittance matrix for this 3-bus case. Now we apply the same method that we learned in the previous slides to a 3-bus network. Now the best approach is to first fill off diagonals. First, for every connected pair, we would put negative y ij. So between bus 1 and bus 3, we have y13. So we would put negative y13. This is the whole example. So you can see between bus 1 and bus 2, for example, we have negative y12, which is negative y12. Now, for between bus 1 and bus 2, again we have negative y12. This is between bus 2 and bus 1. Now between bus 1 and bus 3, we have negative y13. You can see down here. Between bus 2 and bus 3, we have y23 or negative y23. We can put it here. And again, bus 3 and bus 2, you have negative y23. When we have done the off diagonals, we continue with the diagonals. To compute each diagonal as the sum of all admittances touching that bus plus shunt terms. So we have to find everything that is connected to this bus, for example. So for bus number 1, we have y11 plus y12 plus y13. So all of these which are connected to bus number 1. Same thing for bus 2. We have y22a, y12, y22b, and y23. So y22a, y22b, y12, and y23. And finally, for bus number 3, we have 1 connected to the ground, so yn3. Then we have y13, y33, and y23. So y33, y23, and y13. Again, as we know, y12 is equal to y21 because we don't have any direction in the admittance, and y13 is equal to y31, and y23 is equal to y32. So we can just replace them, and doesn't make any difference between them. Now, if I add y11, which is the admittance of the bus 1, plus y12, which is the admittance of between bus 1 and bus 2, and y13, which is the admittance of between bus 1 and bus 3. Technically, what this means is all of the admittances connected to bus 1. We get y11. Same thing we're gonna have with bus number 2, and also bus number 3. We can make 3 equations, and we can simplify this in another way as well. So just another way to solve it. But usually having this would make it as easy. Sometimes we need to change it and put different variables to make it a little simpler. Now let's put some numbers and solve it for a bus with numerical values. Now here we have a numerical y bus. We treat it as a verification exercise. We confirm each diagonal correspondence to one line between 2 buses. We confirm each diagonal equals each diagonal which equals the sum of connected branches. So for example, bus 1, we have to compute all the admittances connected to it, and if there is any shunt present in it as well, we add it to the equation. And once y bus is correct, we can move to the power flow. Now that the network model is set, the power flow is about enforcing power balance at each bus, and we will write equations that relate PQ to the unknown V and T. Now let's solve this. So first, let's put the numbers. The number for the admittance between bus 1 and 2, which we call it Y12 or Y21, both of them are equal again, is going to be equal to negative Y12. And here Y12 is negative J4. So negative J4 gives us J4. The admittance between bus 1 and bus 3, it's Y13 or Y31. In other words, it's negative Y or lowercase y13. And this admittance is negative J6. So negative J6 gives us J6. And finally, the admittance between bus 2 and bus 3, we have Y23, which is equal to Y32, which is equal to negative lowercase y23, which is this admittance here, which is negative J10. So negative J10 gives us J10. So these are the off diagonal admittances that we calculated. Now let's go to the diagonal ones, meaning the admittance, all the admittance connected to bus 1, all the admittance connected to bus 2, and all the admittance connected to bus 3. Now for all the admittance connected to bus 1, we have Y11, which is going to be J1, the shunt, negative J4, and negative J6. So we have this one, and this one. Now adding these three, because all of them are imaginary numbers, we can easily add them. It's going to be equal to 1 minus 4 minus 6 gives us negative 9J. Now the next, we want to find the admittances connected to bus number 2 for the diagonal one. So Y22 is going to be J1 plus J2 plus negative J4 plus negative J10. And we add them together. It's going to be J1 plus J2 minus J10 minus J4 gives us negative J11. And finally, all the admittances connected to bus number 3, we have Y33 is equal to negative J4 connected to the ground, J2, the shunt, negative J10, and negative J6. So when we add them together, negative J4 plus J2 minus J6 minus J10, we get negative J18. Finally, we can write the matrix, and the matrix would be as follows. These are the diagonal ones. We had Y11, Y22, and Y33. So Y11, Y22, and Y33. Y11 is negative J9, Y22 is negative J11, and Y33 is negative J18. And then we have the inductance, the admittance between two bus, between bus number 1 and 2, Y12, we have J4. So J4 here and J4 there. Because again, Y12 is equal to Y21, Y12 and Y21 are equal, we just fill them with J4 the same. Now, the admittance between bus number 1 and bus number 3, it's going to be equal to J6. So again, J6 here and J6 here, Y13 and Y31. And the admittance between bus 2 and bus 3 is J10. So it's going to be J10 here and J10 over here. So that's it for the matrix. Now that the network model is set, the power flow is about enforcing power balance at each bus. We'll write equations that relate P and Q to the unknowns V and theta. Now, power flow computes the steady operating conditions of an interconnected grid. Given specified loads and generator set points, it produces bus voltages and angles. line real and reactive flows, losses and overloads. This is the starting point for many higher level studies as well. Now, you can read faster than I can here. Power flow is numerical analysis of the flow of electric power in an interconnected power system, as mentioned. Load is a static quantity, does not flow. It is the power that flows through the network. Basis for various power system studies, planning, operation, economic scheduling, and stability. Now, in transmission, we usually assume balanced three-phase operation and use a single phase per unit model because it's easier to solve. And it has good accuracy for most planning and operations. It's easier to compute and it's going to simplify our software as well. In distribution, feeders are often radial and can be unbalanced with higher R to X. So specialized methods and tools like OpenDSS are common. So we have same physics but different modeling assumptions and numerical techniques. Some algorithms for distribution systems include the backward-forward sweep algorithm, and it may be a three-phase on-balance system, so we can use a per phase, per unit model, and because per unit you need to have a balanced system. And OpenDSS developed by EPRI are free and open source, so we can use them. Now, this slide shows the power flow model and what is a node breaker model and a bus branch model. Node breaker is the detailed physical representation of a breaker, switches, bus sections. Bus branch is the simplified electrical representation. A bus is connected by branches. Power flow algorithms are typically based on bus branch because the equations are written per bus and branch. Now, this is showing a bus with bus I and J connected, and we want to find the power flow from Y to J. And here we want to first go from Zij to Yij. In other words, we want to go from the impedance to admittance. Lines are usually provided in impedances, which is something like this. Zij is equal to Rij plus Jxij, the real part, and the imaginary part. The real part is the resistance, and imaginary part, because we have inductance, it's going to be the impedance of that inductance. We can have a capacitor or impedance. So for nodal analysis, first we convert Z to Y, and as you know, Yij is going to be equal to 1 over Zij, or in other words, it's going to be Gij plus Jbij. This inversion is where we get the real and imaginary parts used in power equations. Now, the definitions here, we define the line current from I to J as Ij is equal to Yij times Vi minus Vj, which is the difference between them. So using the Ohm's law. And as mentioned, Yij is Gij plus Jbij, and you can find Gij and Bij using these equations. Now, here we define the line current from I to J as Yij, as mentioned, is equal to Iij is equal to Yij times Vi minus Vj. This is technically the Ohm's law. It's I is equal to V over Z, and Z is 1 over Y, so we can write it as the admittance times the voltage. Then the complex power flow is Sij is equal to Vi Ij conjugate, and we can write it expanded like this. Sij would be equal to Pij plus Jqij. Now remember, voltages are phasors here, so Vi would be equal to the magnitude of Vi with the degree of theta I, and we can write it as a complex form. It's going to be Vi cosine of theta I plus JVI sine of theta I, or in rectangular form, Vi real plus JVI imaginary. Now Vi real is going to be Vi cosine of theta I, and Vi imaginary part is going to be Vi sine of theta I. Note that all the variables are phasor variables represented by complex numbers. That's the reason we emphasize on complex numbers in this course as well. So Vi is going to be 3 plus J4, and it's going to be, for example, 5 volts with an angle of 53.1 degrees. And note that radian is used for phase angles rather than degrees in the per unit system. Now, from Sij equal to Vi Iij conjugate, we expand the expression in polar form. The key outcome is that line flow depends on Vi squared terms, which are local, and Vij terms, which are the coupling voltages that we have. Now, if we want to find the real power and imaginary power here, now in this particular example, these are the standard AC line flow equations without line charging. You can see a clear structure. Pij and Qij are nonlinear in voltage magnitude and angle. The most important takeaways here are the angle difference matters a lot for real power, and voltage magnitude affects reactive power strongly. So if we expand this, we want to just multiply these, the first term would be the real power, or P, and the second term, which is the red one, the purple one, is P, and the red one is Q, which is our imaginary. So now if we expand that, Pij was be Vi squared Gij minus Vi Vj, Gij cosine of theta Ij plus Bij sine of theta Ij. And Qij would be equal to negative Vi square Bij plus Vi Vj Bij cosine of theta Ij minus Ji sine of theta Ij. Now this slide reinforces that once the bus voltage and angles are known, line flows are straightforward to compute. So the main computational challenge is solving for V and for theta that satisfies the power balance of the bus. Now consider flow from J to I. If we consider flow from J to I, Pij would be negative Pji, but the real line's resistance causes the real power loss here. So Pij plus Pji is positive. That sum is the real power loss in the line. Physically, it corresponds to I square R. Now, for the real power loss on line I and J, as mentioned, delta P is going to be Pij plus Pji, which is greater than 0. And when we have no loss, delta P would be equal to 0. In other words, Rij would be equal to 0. We have no impedance between the lines. Now, for longer lines, We include a shunt capacitance using the P model. The reason is for a long line, we have capacitance between the lines and the grounds and between the lines as well. So what we're going to do, we're going to add these two shunt capacitance, and this creates what we call a P model that introduces a charging susceptance term of JBK over 2 at each end. This primarily affects reactive power and voltage behavior. It doesn't affect the real power because again it's capacitor. So the average power loss would be 0. So the current expression gains a charging component, and the reactive flow equation includes additional VI square terms from the shunt. So you can see we add the VI, the BK over 2 and the VI square term. Again, it doesn't have any effect on the real power, and only affects the reactive power. Now we have another concept which is called the power bus injection concepts. You can see here if other lines are connected to bus I. Instead of talking about one line at a time, we now define power at a bus level. The complex power injection at bus I equals the sum of the complex powers on all branches connected to bus I. This is what we use to enforce power balance at each bus. Now here, instead of having one power, you would have to find the combination of all of them, the summation of all of them. For this case, what is the power injection from bus I? Let's go to the next slide. The nodal power injection from bus I would follow the equation. We have to find the summation of both the real and the reactive powers. Now, these equations compute PI and QI at each bus as a sum over neighboring buses. They are nonlinear because Vij and VI-Vj products and sine cosine of angle differences. This is the fundamental set of equations that power flows solves. Again, we have it for the real power, reactive power, and we have the sine cosine. And here, conductance GII is equal to negative these sigma of Gij, and BII would be negative sigma of Bij. Now here n is the number of lines connected to bus I. In these two equations, Gij and Bij represent the actual conductance and susceptance of line Ij. What if we use the element in the nodal admittance matrix bus? Then we use these Y bus elements. The nodal power injection equations with Y bus elements would be as follows. Here we write the same bus power injection equations using the Y bus elements Gij and Bij. This is how software typically implements power flow. First we build the Y bus, then we compute P of V and theta and Q of V and theta from Y bus, and then finally we solve the mismatches. Now for transmission lines, Gij is equal to negative Gij lowercase and Bij is negative Bij. Again, n is the number of lines connected to bus I, and Gij and Bij represents the elements in the nodal admittance matrix Y bus. Now, is there any other model methods to drive nodal power injection equations in terms of Y bus elements? Yes, we can do that as well. Now, at each bus, we separate generation and demand. The net injection here is Pi, which is equal to Pij minus Pid, and Qi is going to be equal to Qg minus Qd. So These buses typically have negative net injection, and generator buses have positive net injections. Again, load bus typically have negative net injection, and generators have positive net injection. Here, SID is our load at bus I, and SIG is the generation as bus I. Now, nodal power injection again. Here we have the generation and the load, and the nodal power balances equations are as follows. Now, the power flow problem is that for each bus, the specified net injection must equal the injection computed from network equations. In practice, we form mismatches using delta P and delta Q and solve until they are near zero. So we are solving a system of nonlinear equations. And we have to solve these two equations for the real power and the reactive power. Now, a method to solve this is called the Newton-Raphson method, and this represents the standard robust method for AC power flows. We start with an initial guess for V and theta, and we compute P and Q using that initial guess. And for mismatches, we build the Jacobian, and I would explain about that, and update the state. We repeat until mismatches fall below a tolerance, and that tolerance is determined by the operator. One thing to note here is that iterations updates angles and magnitudes systematically. SI denotes the set of buses that are directly connected to bus I plus bus I itself. And for nodal power balance equations, as previously had, we have PI is going to be PI of the generation minus PI of the load, and QI is going to be the same, QI of generation minus QI of the load. Now, the inputs and outputs in the system must be determined as well. Before that, we have to do some clarifications. Buses are categorized by which quantities are specified. We have PQ bus. We have specified P and Q. So P and Q are specified, known. And V and theta are usually unknown. So most are purely load buses, and here V and theta are unknown. Then we have PV buses. We have specified P and V, and we have unknown Q and theta. These are typically connected to at least one generator. Then we have slack bus, angle reference bus, swing bus, and we have specified V and theta, unknown P and Q. We need a slack bus to set the reference angle and absorb the mismatch due to losses. Now, bus type switch examples would be PV bus to PQ bus when the QG exceeds the Qmax or Qmin, and I'll explain about this later on. Now, the inputs and output summary are shown in this graph, charts, and the slide. Now, the inputs are network data, topology and parameters, bus specifications, generators, set points and limits. Outputs are bus voltage and angles, line flows, losses, and whether any constraints, voltage limits, thermal limits, or reactive limits are violated. And you can see the input information, the tool software power flow algorithm, and the output results. Now, another method that was initially used is called the Gauss-Seidel, which is an older iterative method that updates bus voltages sequentially using the most recent values. It's simple and educational, but slower and less robust than Newton-Raphson method, especially for if we have large or stressful systems. And this slide shows some advantages and disadvantages with the systems. We have divergence issues may not converge with unusual network conditions, compensated transmission lines, and determination of the initial points is critical. And some advantages are very little memory requires and straightforward to implement. Again, but it's not good for large and stressful systems. Stress systems. Now, the holomorphic embedding method, or HEM, which is a newer approach presented as a deterministic alternative. Instead of iterating like Newton-Raphson, it reformulates the problem using a mathematical embedding technique to reach the solution directly when it exists. For this class, the main point is awareness that alternatives exist beyond classic iterative solvers, but again, we don't gonna go deep into them. It was invented by Antonio Trias and has been granted 2 U.S. patents in 2009-2011. We have the direct method, non-iterative, fully deterministic, like DC power flow method, and it solves full AC power flow problems. And the factorization of the admittance matrix is on only once, mathematically guarantees a solution if feasible. Now, common power flow approaches include Gauss-Seidel, Newton-Raphson, fast decoupled DC power flow, and methods like HEM. Newton-Raphson is the most common for accurate AC solutions, while DC power flow is a fast approximation when we only need rough real power and angle behavior, and we don't want to find like exact and accurate ones. And again, we're just gonna go maybe through one of these, the Newton-Raphson method. And that's it for today's class. Just to wrap up, we learned how to build admittance bus or Y bus, how line flows and bus injections are expressed in terms of V and theta, and how the power flow problem becomes solving nonlinear balance equations. In next lectures, we'll go deeper into Newton-Raphson and work through an example iterations. As mentioned, this is it for today's class. If you guys have any questions, just please email me with your questions, and have a great weekend. Thank you and bye.